the only one today?
We hope that Amanda will show up. She normally does. She may be
Okay.
in class or something. We're running late a little bit. Okay. So I'm recording this. So let's go through some concepts because I want to make sure that they are recorded and they're all clear. To approximate the area under the graph, we use these methods. What are those methods? It's okay if you're wrong. Just tell me what you think.
We could use what's it called?
Left.
Left to right, middle.
Yes.
And
Leftmost
right.
point. Right. So to approximate.
Yeah.
Rightmost point. And midpoint. In Calc 2, we're going to add 2 more. Simpson's rules and trapezoidal rule. Okay? But for now, we have these. And this is the best approximation. To find the exact area now under the graph, we use these methods. What are they?
Indefinite integral.
You mean definite. Definite. Fixed, right? Definite integral.
And what else?
The other one, so this is number 1. Number 2 was the one before this one. Sorry. The limit.
Oh, it's just like it's the limit one, where as it approaches infinity.
Yes, of the
Limit
Riemann. Yes.
Yeah, Riemann.
Riemann sum. Yes. We don't want this because we are restricted to linear, quadratic, and cubic. But it's possible. But we prefer the definite integral. Okay. Now, again, let's make up a function, any function you want, and let's find the derivative. And then the differential.
I guess 6 minus e to the power of x all squared.
Okay. Excellent. Good. So let's find the derivative of this.
Is that
2. 6 minus e to the x times?
Yeah, times just e to the x.
A to the x. Awesome. That's it. That's the derivative. Perfect. How do I find the differential and what is the notation?
Pretty sure it's f.
It's dy.
Dy is
so f prime of x, and then this is dy.
Times dx.
Exactly. So it's the same thing. 2 e to the x, 6 minus e to the x, but it has to be multiplied by dx. Awesome. That's the only difference. Perfect. Fundamental theorem of calculus part 2. First of all, what type of function must this be? Only 4? Because if it's not, I cannot use FTC.
Oh, only for continuous.
On the given interval. And what is the answer?
It's like f.
But it has to be uppercase of, yes.
Uppercase f, a, or yeah.
A to b. Yeah. I plug in b.
F of b minus f of a.
F of a.
Or capital.
Yes. So if this is f of x, I have to use uppercase f of x. Good. Perfect. Yeah. Awesome. There are types of integrals.
2, 3.
Definite, which is the integral from a to b from f of x dx, which is a number. The result is a number. And indefinite, which is the integral from a to b from f of x. It has no limits. Sorry about that. So it's the indefinite from a to b from f of x dx, which is the most general antiderivative. And how do we write that? Because we already wrote that, the first one.
Capital F plus C?
Yes, plus C. Excellent. Good. The most or the?
General.
Yes, the most general
antiderivative.
Antiderivative.
Indefinite. Or actually.
Yes. or the indefinite integral. And it's the same thing, so the integral from a to b.
You did it again. Yeah, it's just regular.
F of x dx, uppercase f of x plus c. I did it again. When using the substitution rule for definite integrals, we have to
isn't like
find new limits of integration. We have to find new limits of integration. Good. And for indefinite integral, we have to
isn't like
go back.
To the same.
Yes.
Go back.
To the initial.
Initial variable.
Yes.
Or no, letter.
Yes, variable. Sigma notation and 4 formulas. The sum of 1, the sum of I, the sum of I squared, and the sum of I cubed. These
and
have to be, yes. Of course, all of them are from I equals 1 to n. 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 The first one is n.
Yep. I think the second one is like
n plus 1 over 2. This one is easy to remember because it's the same but squared.
Yep.
So n plus 1 divided by 2. Of course, you will write it as n squared, n plus 1 squared over 4. This one is the most cumbersome one because it's n plus 1, so the same start, but 2n plus 1 over 6. So n plus 1 are the same, but there is a 2n plus 1 and the denominator is 6.
Got it.
Okay. Last one. We can or we cannot always find the antiderivative of a function.
We cannot always.
We cannot. Yes, that's the big problem. We cannot. We wish we could, but it doesn't always happen. Awesome. So now going back, I would like to talk about FTC Part 1. Fundamental Theorem of Calculus Part 1. Okay, so we looked at FTC Part 2. In Part 2, we already know, we wrote it 3 times already. The integral from a to b from f of x dx for a continuous function on the given interval. We have f of b minus f of a, where f is the antiderivative of this function. Now, what is Part 1 teaching us? So Part 2 was teaching us how to evaluate a definite integral. How? Find the antiderivative, plug in b, and subtract when you plug in a. So that's Part 2. We used it over and over already. Part 1 teaches us something else. What is it? That differentiation and integration are inverse operations. Inverse operations. Okay. So how do we illustrate this? Let's take a look at a function. Of course, it's a continuous function, and I'm going to call it f of t. So this is t, and this is y, and this is the origin. Okay, I do have our special interval. So if I want to determine this area, again, how do I determine it?
Definite integral.
Yes, the integral from a to b from f of t dt. This time we don't want that. It can stay there, but this is not what we are trying to do at this point. So again, we're talking about FTC part 1. Now, let's assume that I have x, a number anywhere between a and b. So x can be here, and if it's here, if I want to determine this area, what will that equal to? So this is A, I'm going to call this A1, so not to be confused.
It has to be less than, or it should be the integral between a and x.
Exactly. Still from f of t dt. I'm going to call this x1. What if now x is here? Because it can be anywhere between a and b. Let's say I have here x2. And now I want to determine this area. I'm going to call it A2. From here till here.
It would be just the same thing, but x2.
Yes. So the integral from a to x2 from f of t dt. And I can continue forever. Now, this is a number. No question about it. But these cannot be numbers unless I know x. So if x is a, I know the answer will be 0. If x is here, I know the answer will be, I don't know, 5. If x is here, the answer will be 10. If x is here, it will be 15. If x is here, it will be 25. What did I create with a1 and a2 and so on and so forth?
A line?
I created a function.
Function, yeah.
Because for x being a, I'll say 0. For x equals x1, I don't know, 5. For x equals x2, I don't know, is 10. For x equals x3, I don't know, is 15. And I can go on forever. So for every different input, I get a different output. And this is exactly what the function does. So if I have a function, I say, find the value of the function when x is 2, you'll give me an answer. When x is 3, you'll give me another answer. When x is 5, you'll give me another answer. So we created a function. Okay, so let's write the function. Let me see if I passed 20 minutes. Oh, no, not yet. So this is a function g of x, which is the integral from a to x from f of t dt. And you can say, what are you trying to do here? You're talking about part 1. You're talking about that it's teaches us the differentiation and integration are inverse operations, and you're talking about a function. Yes, I didn't get to show this yet. I'm building step by step towards this. Okay, so this is a function. We have never seen a function like this before. So g of x is a function given in the form of an integral. This is totally new. We have never seen this before. We've seen functions like log, like the square root, like the cube root, like exponential, but we have never seen a function. As you see, this is the variable. We have never seen a function that was given to us in a form of an integral. Now, this is what we are going to do. We're going to differentiate. We're going to differentiate this part, and we're going to differentiate this part. So I'm building towards this. So I have a function that is given to us in the form of an integral, and I'm only asked not to solve. It's a function. I cannot solve unless you give me x. I cannot determine this ever. This is fixed. I cannot determine it unless you say x is 3, and then I'll give you a number. Or you say x is 10, and I'll give you a number. So this is fixed. This, we can only be asked to differentiate. We cannot be asked to solve anything. And that's exactly what we're doing. We are given the function, and we are asked find its derivative. That's it. So we're finding the derivative. So now part 1 of FTC says, when you differentiate an integral, all you do is you get back the function. Why? Because when you differentiate an integral, you get the function. When you integrate a derivative, you get the function. So when you integrate a derivative, these two operations cancel each other. When you differentiate an integral, these two operations cancel each other, because differentiation and integration are inverse operations. Now, what happens if this is not plain x? So let's say I'm given g of x in the form of an integral, but not x, but tangent x. And you can say, wait a minute, what do I do now? I can only be asked to differentiate. I cannot be asked to do anything else. Well, all I need to do is the same thing. I replace t by tangent x. However, here I should have said times the inner function prime. Why I did not say times the inner function prime?
Because if you differentiate x, it should jump to 1.
Exactly. But here, I cannot say that the tangent prime is 1. So g prime will be f of tangent x, but times the derivative of this function. What is it?
X, or it would be secant squared.
That's it.
X.
That is it.